All right. It is a couple minutes before. It is like just a little bit more than a minute. It is. It is 1 minute before um 11 a.m. Oh my goodness. Uh, yeah, Monday, April 27th. I need to work on words here. This is gonna be an interesting class. Yeah. I, in fact, was using this last hour to. I don't actually have many handwritten notes for chapter 6. I just kind of like to talk through this, but I don't think that works as well for people who can't join live, so I've been writing out as thorough as possible notes, and that actually took up a lot of time, and I wasn't finished with Wednesdays. I just finished about 5 minutes ago. So posted that into Canvas. So now there's PDFs for Monday, Tuesday, and Wednesday class. And we don't have class on Thursday. Ooh. All right. Okay. So yeah. Anyway. Let's move this thingy over here. Okay. Yeah. Welcome. So Monday, April 27th. There's a usual online quiz. It opens and is available for April 28th. That is the day that I think is preferred to do it, but recognizing schedules are the way they are, due on Wednesday the 29th. Also on Wednesday the 29th is a response, and also on Wednesday the 29th, the day before an official date of an exam, is that pre-exam assignment, that math is a process thing, so please complete that as well. There's a homework due on Thursday, as there is every Thursday this semester here. Please, if you haven't started already, please start. Start ASAP. And then finally, Thursday is an exam date, so we will not have a live class session. Instead, the exam will be made available on Thursday the 30th, though you can take, as long as you want. Just be respectful of your own time, I guess. It's designed for an hour, so you can spend a little more if you really like, but I wouldn't spend all weekend working on it. Please turn it in on Monday, May 4th. All right, so we previewed some ideas last time, and I know it was a little more informal because I wasn't working off of kind of many official notes, but I'd like to really dig into the thing that we talked about and try to clear up. There's lots of kind of strange, um, I think, thought processes that people have related to these counting problems. So what is it in a nutshell? A set, let's call it S, is described to you. Somebody tells you about a set, and then based on how it's described, clearly S is finite. Okay, you know you have a finite set, but then what is the cardinality of S? Maybe it's not so clear right away. And the whole point of this chapter, the entirety of chapter 6, is to talk about how could you compute the cardinality of S and maybe break down how many things are in the set into some smaller problems. Just as a quick warning first, all of the sets, all sets in this chapter, in chapter 6, are finite. All sets are finite sets. In this chapter, so we just finished off things about countable and uncountable and business like that, and their different levels of infinity and all that. That's some really difficult stuff. And in this chapter, all of our sets are finite. So if you try to apply any theorem. A lot of our theorems in this section happen to be called rules, but they're theorems. Okay, if you try to apply any theorem from chapter 6 to infinite sets, you can expect 0 points, right? So you earn. I've seen it happen. It happens every semester, so I'm trying to make the warning a little more emphatic than I have in past semesters. People try to do things, even though the theorems clearly all state finite sets in them. So here's an example of one of those theorems. It's a theorem. It goes by the name Inclusion-Exclusion formula. Okay, if A and B are finite sets. Again, emphasis on this word, finite sets. Then the cardinality of the union of the two sets equals the cardinality of each individual set added together, but you have to subtract, in a sense, the overcounting. This only works for finite sets, right? So first of all, we're not going to prove the theorem. It should feel true. I've picked A to be the set 7, 8, 9. So 3-element set, right? B to be the set 6, 7. And if you look at the left side of the formula in the theorem, it's the cardinality of A union B. In other words, the cardinality of, when you take the union of these two sets, 6, 7, 8, 9, and you get 4 as the cardinality. If you look at the right side, you've got cardinality of A plus cardinality of B minus the cardinality of the intersection. And if you take a look at that, well, the cardinality of A is 3, and the cardinality of B is 2, and then the intersection has a cardinality of 1. Right? There's one thing in common. So on both sides, you get the number 4. Okay. The key warning here is to say this theorem. Get what I mean by this theorem, right? This thingy here cannot be used if A or B are infinite. If either of them or both is infinite, you can't use this theorem. Look, it's a theorem or test or whatever, like, has conditions to it, right? Has requirements, if you will. In Calc 2, when talking about the series convergence test, I always talk about requirements. But here, it's a matter of look at the language, right? In order to modus ponens for that to apply, you need to have the conditions satisfied in the if part. So this theorem only works for finite sets. I have seen the following kind of mistake happen. I'm going to do this in red. Example, I have seen this happen. A is countable and B is countable. I'm quoting to you things I've seen happen during exams. A is countable and B is countable, so I've seen people write things like cardinality of A union B. They're trying to apply this formula up here, and they'll say things like this is equal to infinity plus infinity, and maybe the two sets you were told that they were disjoint, and so they'll use this as their argument. So A union B is countable. Right? That would earn 0 points. I mean, this is not an argument for why the union of two sets is countable. It does not hold any water. You can't apply the inclusion-exclusion formula, and we have methods for this that involve bijective functions and all this business. So this is truly made up stuff. It will not be rewarded with points. Maybe beside this small example to convince you that the theorem ought to be true for finite sets, I have a slightly larger example, a little bit more work involved, but I've got capital X is the set of integers from 1 to 100, including 1 and 100, and I'd like to ask how many elements of X. So already the question is like, of the first 100 whole numbers, how many of these are multiples of 6 or 7? So I want to count numbers like 6, 12, 18, so on, but I also want to count 7 and 14 and 21 and 28 and so on. And just as a note before getting started, just to save some calculator work, if you punch 6 times 16 into a calculator, you'll get 96. And 7 times 14 equals 98. So I just wanted to show you 6 times what is the number closest to 100, and 7 times what thing is the number closest to 100. To answer this question, I'd like it to fit in the format of the theorem that we have up here, the inclusion-exclusion formula. So I would like to introduce a set A and a set B to you, and more than anything, practice good notation. Part of the thing is, it's one thing to just have you do proofs where you use and prove whether a specific thing belongs to a certain set. But part of the process of talking this language and the metacognition of this is that you need to also practice describing your own sets. And you might need to write things like, sets using the standard grammatical, the notation for this. So I'll go with, we're going to define to answer this question and have it fit the notation of earlier of the theorem we just saw. How about let's define capital A to be the set of all little x in capital X. Capital X is over here. All the integers from 1 to 100, satisfying the property that x is a multiple of 6. I mean, that's just other language for 6 divides x. And we could define B to be the set of all x's in capital X, where x is a multiple of 7. So here we are describing a set, two different sets. We're describing a set A and a set B in the set builder with criterion notation. Based on the note just a moment ago, I think you can convince yourself that the cardinality of A is 16 and the cardinality of B is 14. What about the intersection of A and B? So this should be actually the set of t's in X. I just switched the letter just for funsies, satisfying the criterion that t is a multiple of 42. So I picked 6 and 7 because they don't have any common prime factors. And this one we can just, it's written in this format, which is, fine and accurate and whatever. But because there's so few elements, let's just make sure we understand if we're talking about a certain subset of X, right? All the elements have to come from capital X and have to be multiples of 42. There's only 42 and 84. Those are the only whole numbers between 1 and 100, which are multiples of 42. And so just staring at this set, the cardinality is 2. There are 2 numbers there, 42 and 84. So by applying the inclusion exclusion, we should have the cardinality of the union should be the sum of the cardinalities of the individual sets, except we have to subtract 2 because there was overcounting. So represented in the 16 and represented in the 14, the number 42 was counted, the number 84 was counted, but we don't want to count both of those numbers both times. So this overcounting by 2 we had to subtract. That work for everyone? Make sure we're okay. So there's a special case of the theorem that we just saw when A and B are disjoint, right? If they don't share any elements in common. So the special version of that theorem, let's just put this on the top of the next page, it should still talk about finite sets. So if A and B are finite sets, again, this theorem is only for finite sets, then the cardinality of the union of the two sets equals the sum of the individual cardinalities. Normally you have to subtract off the cardinality intersection, but we have disjoints. Sorry, I'm getting too excited. I forgot to even put the word in here. That's one of the requirements. If A and B are finite disjoint sets, so that's a key thing. Normally you have to subtract off the cardinality of the intersection, but disjoint tells you that the intersection is the empty set, so the cardinality would be 0. So you don't need to write in that you're going to subtract 0. This theorem is the key idea behind this sum rule, which was introduced last time. I'll change up the notation just a little bit to hopefully make things a little more uniform today. If a procedure is done by doing either task 1 or task 2, and I just want to clarify because we use this word or certain mathematical ways, so I want to just really clarify right now, but not both. So to do this procedure, you either have to do task 1 or you have to do task 2, but not both tasks. And there are A ways to do task 1 and B ways to do task 2. Then there are A plus B ways to do the procedure. It's almost like the big procedure has the task of there's door number 1, door number 2. You pick one of those two doors. You can't pick both. And then if you pick door 1, there's like prizes in there. How many of them? There's little a of them. If you go behind door number 2, there's prizes in there. How many of them? How many prizes? There's b of them. And so, how many ways could the story end? It's a plus b, right? The thing to do is to think about there's a connection, right, between the theorem just stated and the sum rule. So you should be thinking about these connections all the time. Think in this section, in this entire chapter, you should be thinking about how elements of a set correspond to situations, right? So what I want you to be thinking about, how many ways, what's the connection to just, again, it's all problem dependent, but to put some generic words to it. How many ways are there to choose an element of A union B if A and B are disjoint? So the theorem that was stated at the top of this page and the sum rule are maybe different in their language, but they're trying to describe the same thing. One is very set languagey, and then the other is very situation oriented. But they're trying to describe the same kinds of things. Okay, we also have the following theorem. If A and B are, again, finite sets, finite is key. This time, if the sets are disjoint or not, that doesn't matter. Okay, then the cardinality of the Cartesian product is the product of the individual sets' cardinalities. Okay, this theorem, again, only for finite sets. So just like we had a moment ago, a theorem that related to this thing called the sum rule, now we have a theorem that relates to a thing called the product rule. So these are, again, two different views of the same phenomenon. One, the theorem that was just mentioned, is in set language only. The product rule is trying to put a situational version of this, and it's written in a generic form here, and we'll look at specific examples, sure, in a moment. I've lost my mouse. There we go. Okay, so let me actually try to keep the sum rule on page here as well. So if a procedure is done by doing both task 1 and task 2. Okay, again, here for emphasis, both must be done. And there are A ways to do task 1. This part sounds familiar to the sum rule. And B ways, little b ways to do task 2. Then there are a total of A times B ways, AB ways to complete the procedure, to do the procedure. Okay, just like a moment ago, there was this talk of connection. It's important to think about what's going on here. Why are these really two totally different sounding ways of talking about the same thing? So what is that connection? Okay, well now, choosing an ordered pair in some not vague, but in some generic language now, and then we'll look at specific examples. But to preview it, choosing an ordered pair in A Cartesian B, that's what belongs to A Cartesian B, right? I mean, ordered pairs. by the definitional Cartesian product. This is essentially not good. Okay, let's. Okay, this is essentially the same as choosing in sort of at least a moral sense. Okay, so not exactly equal, but it's the same as choosing an element of A and an element of B. Because that's what's going on in your ordered pair, right? Your ordered pair has first coordinate an element of A and second coordinate an element of B. So the thing to do is, I think the key confusion that occurs, the question that people always want to ask is, when do I use a sum rule versus when do I use a product rule? And I've tried to really emphasize this in even just the parenthetical remarks so far. But the point is, as a general thing you should do in any of these counting problems, if you're trying to decide between sum rule and product rule, is first of all, identify the subtasks. So in the nicest of situations, there's a task 1 and a task 2. Of course, there's more complicated versions where there's a task 1, task 2, task 3. But you should first of all identify the subtasks. Let's just call them right now task 1 and task 2. And then what you want to do in addition is, and also for each of the subtasks, you also want to figure out this and the number of ways. And the number of ways to do each subtask. Okay, so the number of ways to do each subtask, we in both the statement of the product rule and sum rule we have, those are the little a and the little b. And then you need to answer this question. Like people, I have asked people, previous semesters in office, I was like, okay, are you going to use a sum rule or product rule? And they just kind of pick one at random, it seems, without answering this question. This is the key question. Do you have to do both subtasks, task or subtask? Okay. Do you have to do both subtasks, or can you only do? And by can you, I mean like really may you? Are you only allowed to do one subtask? That's the key difference, and it's in the language of the sum rule and the product rule. And it all goes back to, think about if you had two disjoints for the sum rule. Think about if you had two disjoint sets A and B that are finite, and you union the two together, picking one element out of A union B. Well, you either pick an element from A or you pick an element of B, not both. Whereas for if you're picking something from the Cartesian product of A and B, it really it amounts to picking an ordered pair, and that since there's any possibility from A for the first coordinate, any possibility of B for the second coordinate, that's how many total you can have. So what we're going to do, and of course it's all strange. The mouse. Oh, this is not good. Hang on a second here. Let me see if there we go. We're going to spend a little time in a bit of worksheet mode. So what I'd like to have you do, I hope this is large enough on screen, and I did post this in Canvas if you'd prefer to see it there. I've got 5 counting questions here. In each case, I'd like you to identify the subtasks, and then, as was mentioned just now, for each subtask, identify how many ways that subtask can be done, determine if the sum rule applies or the product rule applies, and then answer the counting question. So I'll give you some number of minutes to work on this. Feel free to ask questions to each other or to me, or you want to check on something. No, 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 no. Okay. Sorry, this stylus is running out of batteries and I have this backup, but it's not as good. I can't even close this one now. Oh, jeez. All right. No! Gotta align this just right. So for the first question, there are 2 soup choices, 3 salad choices. At least the intention of the questions, all of these, not all these things are said so completely in these questions. So sometimes counting questions can sound a little vague, but you are just try to figure out the intent. The idea here is you choose a soup or a salad, but not both, even if that language of but not both wasn't explicitly said. So this should be a 2 plus 3 kind of situation. That's what I hope you saw in question 1. In question 2, the names of the options were not even given. It's another restaurant situation thingy here. But if you choose from one out of the 3 first course items and then choose from one of the 4 second items, that should be a 3 times 4 situation. Product rule applies because you have to make both choices to make the meal. Let's scroll down on the page a little bit here. For numbers 3 and 4, a question came up. Is it assumed that the same number can be chosen for each entry? Good question. Yeah, I should have included that because the question's a little unclear. Yeah, the combination lock could use the same number for the first entry and the second entry. So like 1212 would be a valid combination, a valid password, let's say. I'm trying to avoid the word combination because there's a technical meaning to the word that we'll see a little later today, in fact. But a valid password could be 12 for the first spot and 12 for the second spot. And for question 4, similarly, you can have 12, 12, 12, or 8, 8, 8, or 31, 31, 31. Those would all be valid for problem 4. Thanks for that, asking that for clarification's sake. And like when you buy one of those combination locks, that can happen. I was trying to actually pull that up. I was gonna pull up one of those standard like locker ones but this mouse is also running out. Everything that I have here seems to be running out of battery, so I'm just gonna try to not mess with things too much right now. Okay, so I hope the question 3, if you make a password by choosing one out of the 40 numbers, and then by choosing a second, you've got to choose one of the 40 numbers for the first spot and choose one of the 40 numbers for the second spot, so that you have to make both choices. It's not just one or the other. So I hope you're seeing that in question 3, the product rule applies, so it should be 40 times 40. Of course, you could call that 40 squared. The next one, question 4, should be like a product rule multiple times idea, right? So this should be a 40 times 40 times 40, in other words, 40 cubed. And that actually, those traditional little dial locks, I don't know if you used one of those in high school. That's how many combination locks there are in total. You can't have more than that. Um, see, a library has 700 fiction books and 800 nonfiction books. If a patron can only borrow one book, then how many ways are there to select a book from the library? Again, you're only one or the other, right? So this sort of this. I hope you're seeing this 700 plus 800, right? Just stick all the books together. Who cares which are fiction and nonfiction? Almost is the idea here. Now, I would challenge you to do the following. Not necessarily right now. Maybe you already did if you had some time to think about it. Is I want you to come up with two counting questions, right? It's like both of the questions just to fix numbers here. You could change this up later if you want, but you could think both questions should have two subtasks, and the first task has three options, and the second task has four options. And I want you to think of how would you word your question so that the final answer to one of your questions is 7 and the final answer to your other question is 12. I mean, think about like trying to create questions where the sum rule applies for one question and the product rule applies for the other question. And the challenge would be how similar could you make the questions sound to each other? Like, could you be tricky? Could you like really try to make it hard for somebody else to figure out? If we were in class, I would have you in groups and have you write questions and challenge each other with this. But I think for the sake of timing, I'm going to leave that. And so this process of you coming up with a question is thinking of this backwards, and it's actually a thing that we will be doing quite a bit of early next week. So I just wanted to get that idea on your mind right now. Just to try some other things though, I'd like to kind of think about this. So how many bit strings of length n are palindromes? Palindrome being a thing that's the same when you read it forwards or backwards. So as an example of a bit string that is a palindrome, like 1101 000, then 1011. So whether you read that forward or backward, you get the same string. So here's the thing. As just a bit of informal discussion, and you'll find that a lot of these counting problems tend to have lots of very informal sounding discussions compared to all the very formal things we've done. There's ways to do this all more formally, but we'll take an informal approach. It saves us a little bit of time here. When n equals 3, a bit string, let's call it little b, can be written as b sub 1, b sub 2, b sub 3. What I'm trying to get sorry, that's poorly. Again, this pen is not as responsive here. B sub 1, B sub 2, B sub 3. So little b equals this, okay, where those are the three positions, and each of the b sub whatever, so b sub I, has to be either a 0 or a 1. So it has to be an element of the set consisting of 0 and 1. There's a total of, by the product rule, 2 times 2 times 2 bit strings overall. But if b equaling b sub 1, b sub 2, b sub 3 is a palindrome, then not all 8 of those will count. Right? So I'm just mentioning the 2 times 2 times 2 just as a side comment to clarify there's 8 total bit strings of length 3, but to have a palindrome, b sub 1 has to equal b sub 3. Right? B sub 2 just has to be equal to itself. Right? So we actually have two choices for b sub 1, and then b sub 3 is just going to copy that. So let's not even think of those as new choices. There's no choice there. And then two choices for b sub 2. So you pick one of the bits for b1. B1 you pick either a 0 or 1. For b2 you pick either a 0 or 1, and that's it. And then that will create automatically the palindrome, because the third bit position should just copy what was the first position. So there's a total of 2 times 2 bit strings which are palindromes. And again, I wanted to write 2 times 2, not 2 plus 2, right? Because the idea of the product rule that in position 1, you pick one of the two options independently from in position 2, where you pick one of the two options. As sort of a um, like, let's look at what about if you had n is equal to 8? Then there's these 8 positions, 1, 2, 3, 4, 5, 6, 7, 8. And instead of writing b sub 1, b sub 2, b sub 3, b sub 4, if you had p, q, r, s, then it has to end s, r, q, p. So there's 4 choices in the end. So 2 times 2 times 2 times 2, or 2 to the 4th, palindromes. If n is equal to 9, it gives you like a p, q, r, s, t, s, r, q, p. So there's 5 independent choices you make. So 2 times 2 times 2 times 2 times 2. Right? If n is equal to 10, then you p, q, r, s, t, and then you repeat t, then s, r, q, p. So you have 2 to the 5 again. Whoa, that's kind of strange, huh? You have, and then when n is 11, you have 2 to the 6th palindromes. When n is 12, you have 2 to the 6th palindromes again. So look at this kind of repetition. There's a way to describe this. So I want to preview an idea that you'll see more of late next week, but there are 2 to the power, and then this exponent is n over 2 with this notation, palindrome, bit strings of length n. And now maybe your question is, what the heck is this thing? The fraction n over 2, why is it surrounded by this thing? What is that? To help clarify this, here's an informal definition. So I'm not going to ask you to define this, later, but like I want you to have seen this definition. If you have a real number x, then the ceiling I'll give the notation right after the thing being defined here. So you take the real number, you surround it in this notation, looks like 2 little hooks like this. The ceiling of x is the smallest integer. C satisfying x is less than or equal to c. Okay. So if you have a whole number, then the smallest integer would just be that number. But if you have a number that's got some decimal expansion, you just kind of keep raising the number up until you get to a whole number, and because that'll be the smallest integer, which would satisfy this. So all the time when looking at these problems, it's important to think about, does the product rule apply or does the sum rule apply? And in fact, what we're going to do right now is build into some preview ideas that we will clarify tomorrow, but I want to get your feet wet and actually still practice things like product rule versus sum rule as much as possible in talking about things called permutations and combinations. So just as a preview problem, we're going to try this. So we have the product rule and we have the sum rule. Always think about which apply, but how would we modify one of these? How could we let's not say modify these. How could we create an altered version of one of these to answer the following question? So what I'd like to do is let's answer this. A banking pin personal identification number consists of 4 digits. But let's just say this bank specifically says, but all 4 digits must be different. I don't think any bank is actually that strict about it, but Let's just say right now, and it's just included in the question, that that's just how the pin numbers are for this problem. Those are the rules. Then how many pins? How many pins are there total? How many pins are possible? How many pins are there? Okay, first of all, before answering the question, let's just do as a warm-up exercise the idea of how many are there if this must be different restriction is removed. Right? So let's just how many, yeah, create pins, and it doesn't matter now, like, so this 4 digits must be different, meaning like 1, 2, 3, 1 is not allowed. But now if repetition is allowed, then 1, 2, 3, 1 is fine. And so is 3, 3, 3, 3, for example. So if we remove this restriction of must be different, then to create a 4-digit password, you have to pick one of the 10 numeric digits for the first location, and the second digit or the second location, you've got to pick one of the 10. So you have to pick in all spots, right? You can't just pick what the third digit is, and that's it. So it's not the sum rule, right? I want you to see this as 10 times 10 times 10 times 10. To really write it out like that right now, it emphasizes that it's the product rule, but we can just write this as 10 to the fourth. Right? That's how many pins there would be without this restriction of different. Like, they just don't have to be different. But what if we go back then to answer this question? Right? So, let's think about how we're going to have to modify the product rule a little bit. I mean, the product rule is the product rule. But based on that rule, can we figure out what we should do to create to count how many possible pins that there are if you never have the same digit reappear in your pin? Well, for the first position of your pin, there's 10 possibilities. But now, whatever you pick for the first coordinate, first entry of your pin, you don't get that choice anymore. So maybe you picked a 7. It doesn't matter what. But like if the first thing in the pin is a 7, then your second digit can't be a 7. So you have a total of 9 remaining choices. Right? So there's one fewer choice. That's why there's a 9 here. So if you picked a 7, then you can't pick a 7 anymore. And then let's just say the first digit was a 7. I hope I'm not stating anybody's pin as we go through this. And then the second digit of the remaining 9 choices, let's just say you pick a 0. I don't know. Then you've used a 7, you've used a 0. Those can't be used anymore. So there's only 8 remaining choices. Okay. Right. So there's one fewer choice again. And then 7. Right. So 10 times 9 times 8 times 7. This idea, we're going to run with it tomorrow more, but I want to introduce some definitions that are confusing so that we can deal with the definitions today mainly and then deal with counting tomorrow. So here's a definition. Let S be a finite set. Again, everything we deal with in chapter 6 is finite sets. So a permutation of S is an ordered arrangement of the elements in or of, whichever word you like, in S. An ordered arrangement, one last thing here, and then we'll look at examples. An ordered arrangement of R elements, R being a number, little r being a number, of R elements from S is called an R permutation. Okay, we're defining two things here. We've got permutation, we've got R permutation. And I hope these definitions, I mean both included in this one paragraph, bother you, and that you're like, what the heck is an ordered arrangement? We've not ever used this language, and all of our definitions have always lived kind of on top of something else as being a special version of something else. We don't have this here. So I want you to see this by example, and then I think it'll be kind of mostly okay, and then we will say something else to try to help. So I've got, just for an example, the finite set S is the set consisting of 1, 2, 3, and 4. Then, couple examples I want all, so I'll put 3 bullet points here. So here's an ordered arrangement: 2, 3, 1, 4. This is a permutation of S. Okay, so I've taken the 4 things in the set S and I just put them, again, things in a set are not in order, but this ordered arrangement thing, I just have this comma separated list right here, and I've chosen a specific order: 2, then 3, then 1, then 4. That I've listed all the elements of S, and this is called a permutation of S. Also, to clarify, this same thingy, 2, 3, 1, 4, is a, to include now this R permutation business, this is a 4 permutation of S. And if I just pick 1 and 4, well, I'm not using all the elements, just 2 of them, so here I'm plugging in little r as 2. This is a 2 permutation of S. Okay, this maybe mostly bothers you, and so I'm going to do the following. Let me actually just push this to the top of the next page so that we can compare and scroll a little easier. Here's a definition. There's an alternate definition. Let S be a finite set. Starts off the same. Okay, an element little p in S to the cardinality of S is a permutation of S. I'll leave off the of S here. If every coordinate of P is different. Before, oh wait, well, no, let's just include one more sentence here. An element little p belonging to S to the R is an R permutation if every element of P is different. So, couple comments, right? Yeah, first of all, let's clarify what this is going on in this notation, right? So, this is, I promise, actually nothing new. That's what I'm trying to get at here is you've actually seen this notation. When you have a set, so you have this, looks like exponential kind of notation, but if you have a set as the base, so to speak, and the exponent is an integer, specifically a positive integer, that's, we have a definition. That's the Cartesian product applied multiple times. Right? So this is an R-fold Cartesian product. This is, so for example, if R is 2, S2, this just means S Cartesian product S. And S3 means S Cartesian, S Cartesian, S. So that's, it's an old definition. And the whole point is, I know that the same two words, permutation and R permutation, are defined in this definition and this definition up there. And you're saying, like, what? Why is this okay? And what I'm trying to get at is, either definition is going to be fine. They're technically different. Either definition okay. Now they're technically different because one's just this ordered arrangement up here. But this ordered arrangement business, I think people find it bothersome because we haven't ever had a thing like that. And the only reason to prefer the definition down here is because it connects to all the things that we've done so far. So example, and I'm going to really connect it back to what we have earlier. If you have the ordered 4 tuple 2 comma 3 comma 1 comma 4, in the set of parentheses as an ordered 4 tuple needs to be written, this is an element of S4, and that's this right there. So this is a permutation of S. And again, I'm just trying to mimic all of the examples we have up here. 2 comma 3 comma 1 comma 4. This is a 4 permutation of S. And then if we have ordered pair 1 4, which belongs to S2, this is a 2 permutation of S. Okay, and I should just comment here for a moment. Note that 2 comma 2 comma 1 comma 3, now this is an element of S4, right? It's an element of that fourfold Cartesian product, but this doesn't count as a permutation, right? The thing here to note is, but not all the coordinates are different. So this all the coordinates are different is the thing that's capturing the whole ordered arrangement business where you don't have repetition. All right. Okay. I'd like to look at a theorem that'll count. So the number of our permutations, we actually already did it in the little preview bank pin question. The number of R permutations of a set with cardinality n is, so it doesn't matter what that set S is, it just the number of things in that set S matter, so we're just using little n for that. Here's notation for it, capital P of n comma r. So capital P, thinking of the word permutations, it ends up being, as we saw in our example, well, there were n choices for the first spot, but then the next spot we weren't allowed repetition, so n minus 1 times n minus 2, and so on like this. Keep multiplying, and it turns out the total number of factors needs to be r, and the way that's achieved is actually with the last factor being n minus r plus 1. Think about why that plus 1 is there, but let me just write this another way that's a little more convenient. It's n factorial over n minus r factorial. So as a proof of this, I'm going to suggest that we just write this sort of brief sentence, and then we'll explain it a little more. So there's n choices for the first coordinate, and then there's n minus 1 choices for the second coordinate, and so on. And we're applying the product rule. Now, that proof is maybe a little too short, so I want to include a little more detail that might clarify the confusing thing of how come we have an n minus r plus 1, where the hell did that plus 1 come from is usually the question. So I'm going to just include slightly more detailed explanation. The first factor of the use of this product rule is, I know it just says n up here, but I actually want to write this n, in the format n minus 0. And I know this looks a little funky, but the way I want to write n minus 0 is actually n minus quantity 1 minus 1. And then the second factor of the product rule, we see it up here, it just says n minus 1, right, is n minus 1. But the way I want to write this is n minus quantity 2 minus 1. See, this helps clarify, if you keep following this pattern, eventually the rth factor of the product rule is n minus, well, let's not even write this version of it. It'll be just clearer to write down that this should be n minus r minus 1. Right? So I hope what you're seeing here, let me maybe circle these, is the 1 in the word first appears right there. The 2 in the word second right there. The r is there. And another way to write n minus quantity r minus 1 is to distribute this minus sign, of course, and write it as underlined up here as n minus r plus 1. Okay. Oh, I was going to say something about combination, but I don't have time. I'm going to just end on this last comment here, right? One of the things that I want you to be thinking of actively is, what about product rule as we applied it at the beginning of class today versus permutation? So we're going to get quite a number of counting techniques tomorrow as well. And so the thing that like starting earlier today was sort out product rule versus sum rule. But now think about product rule versus permutation. So what should you ask yourself? What should you ask yourself to sort out whether the final answer to a question is going to be A times B versus a formula that looks like, and I'll just use, I know it says n's and r's up here, but let me just use, to make the comparison, a factorial over quantity a minus b factorial, right? So one of these versus the other as final answer. You've got to think of what kind of decisive question, based on what we just talked about in this section so far, is going to sort out, is it the product rule, the original product rule, or is it this modified product rule, and is it really counting permutations? So I'm trying to use, instead of n's and r's, I'm using a's and b's for it. But you've got to sort that out, right? I want you to think about, when you see a counting question, what kind of questions do you need to ask yourself to sort this out? All right, questions on that? I see my screen blinking, so I'm out of time. But if you had a question or two, I will stick around here to sort the things out.